Good evening. Welcome to the, I think it's the first public lecture for 2014, organized by the Institute for Mathematical Sciences. My name is Chaudhuri, I'm the director of the Institute. And this evening we are very happy to have Professor Probal Chaudhuri from the Indian Statistical Institute. Professor Chaudhuri was a student at the Institute, and after graduation he stayed, it was a master's degree at the Institute before he went on to work in 1985 for his PhD. He received a PhD in statistics from Berkeley in 1980, and then went on to be a faculty member at the University of Wisconsin-Madison, and stayed there for 2.5 years. And according to him, it was quite an experience there. Winter days in Wisconsin.
I will complain about that.
It was obviously a nostalgic experience of feeling. But I suppose he will be quite pleased that he was not there this winter in Wisconsin. Anyway, he has had a very successful career, having done outstanding work in the area of statistics, and is in fact a member of the three major academies, scientific academies in India. Tonight he's giving us a talk. The title of his lecture is Shape of the Earth, Motion of Planets, and then that will lead to the least square method. Please welcome Professor Chaudhuri.
So, good afternoon to all of you, and thank you for the nice introduction. Thanks also for the kind hospitality of the Institute of Mathematical Sciences here. Whenever I have come here at the Institute, I think there is never any opportunity to complain about the hospitality. Everything is taken care of extremely well. I also have occasionally visited the Department of Statistics, and we have to look at the hospital. Their hospitality was also quite remarkable. Everything is very well organized here, which is not the case when you come to India. So anyway, I thought this is a sort of a late afternoon or kind of evening talk. So it should be in a sort of, I felt that it should be not just science, it should have some elements of entertainment in it. Okay, so I planned it like that. So I have chosen a topic which has a very big history. So I don't think I'll be able to do justice to all the things related to the problem here. But I have chosen materials that are probably most interesting to me, and I hope they will be equally interesting to you. So let's start from a point really back in the past. So I will go to sometime in 17th century. This is how this problem sort of started. Okay, and it started probably earlier than that, but let this be the starting point for us today. So it was about the French astronomers. The French astronomers were interested in the 17th century to map the sky in the southern hemisphere. So they were going to South America to take astronomical measurements. And this is the name of a very famous French astronomer, John Riker, who was in South America in 1672. But the problem that he sort of observed has nothing to do with astronomy immediately. Okay? So he saw that two pendulum clocks that he was carrying, which were very well calibrated in Paris, they were losing 2 minutes 28 seconds every day. So when we compared it to the local clock in French land, that was a big surprise. So it's like, I sometimes give this talk to high school students also, a version of this talk. So before I start, I ask them this question, that what do you think is the greatest scientific achievements or most exciting scientific research or discoveries for the last 15-20 years? And I get answers like starting from smartphone to stem cell, nanotechnology, Higgs boson, all kinds of things. And then I tell them, that this was the most exciting problem in 17th century. That why a pendulum clock is running slow in South America. That was the exciting problem. So he brought this problem back with him in 1673 and reported it to the French Academy, and it created a big turmoil. So everybody had their own theory about why it was happening. And it was such an important problem, it involved one of the greatest giants of science. It was Isaac Newton who gave a theory to explain this. Newton's Principia, which came out in 1687, there he was giving a theory for it, and the theory was pretty simple and straightforward. Newton claimed that the Earth's rotation created a distortion in the round shape, in the sense that it became somewhat elliptic in shape. Okay? So it was bulged at the equator and a little flattened at the poles, and so the pendulum will be running slow near the equator because the acceleration due to gravity will be a little less. That was his theory. He had no measurement, no observation. Okay? It was just a theory that he gave. So it's a remarkable thing that Newton could imagine something about the shape of the earth based on this little observation. But this is not something that was well accepted by all the scientists, particularly the French school, where this problem sort of started. The French scientists thought that Newton is wrong and there must be some other reason for it. So it is, in some sense, yet another conflict between the French school and the English school. I mean, with Newton, they always had a fight. There was a fight on the priority of who invented calculus with Leibniz, and this is another fight they had. Now, let's see. Now, if you want to settle this problem today, it's not a problem. Okay, so you can take a satellite image of the earth and decide who's right or who's wrong. So, in fact, I was looking through the net trying to find out whether anybody has taken any interesting picture of Earth which gives a good idea about what is the real shape of Earth. Okay, and I found something. So it is a satellite called CHAMP satellite, which is a German satellite, and it was launched, I think, I don't remember exactly when, but the mission was completed in 2010, and it sent a lot of images of Earth to the German Geophysical Research Center in Potsdam. And if you go to their website, you'll see a lot of interesting images. And I'll show you one image that I have taken from their website. This is how it looks. It's quite interesting, right? I mean, I don't think anybody who hasn't seen this picture would imagine Earth to be something like this. So this is how it looks according to the JAMP satellite image. Anyway, so let's see how they were trying to settle this problem at that time. So it's like a conflict between say two possibilities, whether it is an ellipse like this or something else. Now, if it is an ellipse like this, they came up with an interesting idea to verify that. Okay, this is what Newton was sort of predicting about the shape of the earth. Okay. So the idea they were using is very simple. If you measure the length of, say, 1 degree latitude near the equator and the same near the pole, if the shape is like this, the length of the 1 degree latitude will be more near the pole. Okay. So this is something they could do in the early 18th century, and so that's what they decided. So let's say 17th century and early 18th century, this was one of the biggest research projects. So they decided to take a lot of measurements on meridian arcs, and they wanted to use that to settle whether Newton was right or wrong. And it was the French Academy who took a major initiative in these measurements and the collection of data. It's a very simple idea, and of course, I mean, implementing this to collect data was not very straightforward, because traveling in those days was not very easy. So if you want to cover a meridian length starting from equator all the way up to pole, it is not an easy task. And also taking measurement on the surface of the earth that spread over such wide range is a challenging task. It was a challenging task for them at that time. Anyway, so let's see how they are collecting measurements. Okay, now before I go into collection of measurements, maybe I should tell you some approximations they were using. Okay, so this is a very popular approximation they are using Europe at that time. Okay. So let's say we have length of 1 degree meridian arc centered at latitude theta, and let's call that y. Then they approximated y by this. So y was approximately some constant times sine square theta plus c. I use this usual constant m and c because that's what appears in the linear equation in an analytic geometry book. So roughly it's like there is a linear relationship between y and x, where x is sine square of the latitude. Okay. This was a very popular approximation that astronomers and geodesists used at that time in Europe. Okay. And the ellipticity of the earth was defined to be this quantity. So you see that if m is positive, that means earth has the shape that Newton predicted. Because as you move towards the pole, you get more and more arc length. So near the pole, there will be an excess over what you get at the equator. Okay? And if it's a perfect round, then m will be 0. So that was taken as the measure of ellipticity. And Newton, based on purely theoretical calculation, estimated it to be 1/430. That was Newton's estimate of ellipticity. Okay, that's what Newton said. Okay. Now let's come to the collection of data to verify whether Newton was right or whatever. What is the ellipticity of Earth? So the first mission that was completed in 1720, they took measurements over a range of 9 degree latitude, and this project was led by two Cassinis. You see, they are actually father and son. Domenico Cassini was first the director of the Royal Observatory in Paris, and he was succeeded by Jacques Cassini, who was his son. And their measurement actually contradicted Newton, because see, I mean, the Earth has a very irregular shape. So if you take measurements over only such a small region, you really cannot settle about the overall shape of the Earth. But so Newton had a lot of supporters, even in France. For example, Voltaire was one of the biggest supporter of Newton. Okay? So this controversy continued. This arc measurement in 1720 certainly didn't settle it, and we know that Newton is correct. So a lot of people also believed that Newton was correct. So in 1735, they launched a big arc measurement mission, and this is in the history of science. This is a landmark event. They call it the French geodesic mission. So the emperor of France at that time was Louis XV, and the French Academy convinced him to take a project where they will send a team of scientists all the way to Ecuador, near Equator, to collect measurement. Also, as far as possible close to the pole. So they've set two teams. One team was led by the famous Swedish physicist Celsius, and he was taking them to a place in Scandinavia, in Laplace. So that was closest to the North Pole he could come, and they could come at that time. And then the other team went to Ecuador, and that was a very painful journey because people couldn't fly at that time. Okay, so it was a long voyage that took almost 1 year to be completed, and then they reached Equator, and it took them another year to complete the measurements over 3 degree latitude near Equator. So it was a long and painful project, and a couple of people actually died. And in fact, the route they had taken, maybe I should quickly tell you, because it's quite interesting, the route they were taking at that time. So this is the information that I find about that mission. So the Ecuadorian expedition left France in May 1735. They landed on the Caribbean coast in Colombia, sailed to Panama, where they traveled overland to the Pacific and continued by sail to Ecuador. That's how you were traveling to South America from France in those days. It will probably take you how many hours of flight? I don't know, maybe 12 hours? Not even that long. Anyway, so for 1 year they traveled, and then they collected measurements. But meanwhile, all over Europe there are many other arc measurements that were carried out. And I will show you now an interesting table that was compiled by people on arc measurements. So here is the table. Okay. This is, you see, this is Quito. That is the capital of equator, so that is near latitude, and they measured length of 1 degree latitude arc there, and this was the measurement unit in those days in France. Okay, it was toises, and 1 toise is this much. 1 toise is roughly 6.39 feet. So this is well before the development and implementation of the metric system. So in different parts of Europe, they had different measurement units being used. Just like there was no euro, and there were like different currencies at that time. Okay, so it's like different units of measurement, just like different currencies. Okay, so French are measuring it in toises, and this is how. Let's ignore the last column here. Okay, I don't think it's important for us. So the furthest or closest to the North Pole was this, and so furthest from the equator they could go as this, that is 66 degree latitude. Now this table that I have prepared, or rather I have copied, I have not prepared this table, it was prepared by these two people, Boscovich and Mayer, and this was reprinted in Boscovich and Mayer 1770. Boscovich is another very interesting and important character in this project or research. And he made a lot of contributions in many areas of science, and this is one of his interests. He was actually a priest who was living mostly in Italy and France, and some of the ideas of fitting curves and equation actually goes back to him. He was one of the originator of the basic ideas there. So I will talk about Boscovich in a minute more. Now this to them led to the following problem. Okay, so it's like you are sort of trying to find out roughly a linear equation there. So what is the linear equation there? You have 5 cities there. So if you plot this data and join any 2 points by a line, you get 1 equation. So it's like that you get 10 equations. So people were wondering how to reconcile these lines and how to come up with a common equation here. And they didn't have a clear idea about that at that time. Okay. So Boscovich, here is a picture of Boscovich. So Boscovich is one of the person who first gave a good formulation of this problem. Okay. So I should tell that formulation first before I discuss anything else. So this was Boscovich's formulation. Boscovich formulated the problem like this. So he said, you try to find your slope and intercept by minimizing this. So this was Boscovich's least absolute deviations problem, which is in some sense the first idea or the predecessor of what we call least squares method. Okay. So if I draw a picture, Boscovich was essentially trying to minimize all those sum of vertical deviations. Okay. So this is Boscovich's formulation of the problem. Okay. All right. So Boscovich formulated the problem, but was he able to solve the problem? Not really. Okay. In fact, Boscovich's first attempt to solve this problem was to use calculus. He thought he can use calculus to solve the problem. It is a minimization problem, and calculus was well developed by then. But then when you try to differentiate this, it's an absolute function. So wherever it is differentiable, it will give you plus or minus sign. So Boscovich made a very interesting comment about it. Okay. So this is what I read in Stigler's book on history of statistics, and Stigler has quoted Boscovich saying something like this there. So if you try to differentiate this absolute function, everything disappears. So for him, it's like when you differentiate the absolute function, you get plus 1 and minus 1, so for him everything disappears. And then he says that with that all the hopes of mathematicians also disappear. So that was his comment. Because, for him, when you differentiate, if the variables that you are interested in do not remain, then it's like vanishing. So it's vanishing hope for him. So Boscovich tried various things with that, but eventually he gave up. But he prepared a table where he calculated all those pairwise lines, the pairwise solutions, and prepared a table. This is the second table from Boscovich's work. And so based on each pair, he calculated the value of ellipticity. So each pair was giving him one equation, and he was getting a value of the slope, he was getting a value of the intercept, and from there he was calculating the ellipticity. And then, except for one pair, everywhere you get positive, and there are certain mistakes that Stigler points out in his book. So in some sense, if you look at this table, there is overwhelming support for Newton. In fact, the problem involving Newton was resolved before the Ecuadorian expedition was completed, because once they reached close to the place of Laplace and took measurement there, they realized that Earth is really quite flat. In fact, the way they convinced the Emperor Louis XV is that they wanted to prove that the diameter, rather the circumference of the Earth, if you measure it around the equator, that will be less compared to if you take it around the pole. Now, when people reached Laplace, which they reached much earlier, before people could reach equator, they realized that's not true. So, in some sense, that original project was scrapped by them. Okay? But people still went to equator because they had other astronomical projects, and then they collected measurement and came back. And I have seen that at that time there are many interesting comments from the supporters of Newton, because Newton came out to be a winner in this after this expedition. So, for example, Voltaire prepared a cartoon where he was drawing picture of the Earth as an ellipse, and in the picture there was, I should have taken a copy of that. Unfortunately, I realize now that I don't have it. Okay, so there was a picture of the face of Cassini there. Okay, in that ellipse, and Voltaire said that Newton flattened Earth as well as the Cassinis. So that was Voltaire's remark about Newton after this. So anyway, so this was one problem that Boscovich really couldn't solve. He worked on this problem for a pretty long period, till 1770, but never could come up with a solution of this problem. And he was certainly not thinking about Lisp. For him it was Lisp absolute deviation, and he was searching for a solution for that. So he essentially left the problem at that stage, in that table, and he made some remarks that he finds all these ellipticities widely varying. So is Earth really an ellipse? He made some comments about that, which is reasonable, because there is indeed, if you look at it, look at these values of these ellipticities, there is a wide variation, that is clear. Okay, now let's come to the second problem. Okay, so the second problem is, as I said, it is about the motion of the planets. Okay. Now, if you look at the solar system, there are two reasons why I have brought this picture. The first reason is this. You look at Jupiter and Saturn. Jupiter is the largest planet, so it was very easily observable for a long time. And Saturn is also very easily observable because of its size as well as its rings. So, for centuries, people had taken measurements about their position and motion. So it was so I'll come back to this picture again. So it was in 1676, this famous astronomer from England, Edmund Halley. We all have heard about Halley's comet, so this is that astronomer, Edmund Halley. So he was looking at the data on positions of Jupiter and Saturn, which was, as I said, tabulated over centuries by astronomers. Okay? And he found something very surprising. He observed that there is an acceleration in the mean motion of Jupiter and a retardation in the mean motion of Saturn. So it's like this, that if you follow the orbit over time, the orbit is, for Jupiter, the orbit is sort of shrinking. Whereas for Saturn, the orbit is expanding. It's kind of a very surprising thing, because what does it mean? I mean, does it mean that eventually Jupiter is going to collapse into the sun and Saturn will disappear somewhere in the space and the solar system will completely collapse? So this became again another exciting problem around the same time. You see, this is 1676, whereas Riker's problem was around 1672-73. Okay. So it was such an exciting problem that the Academy of Science in Paris announced a prize for it in 1745. If somebody can give an explanation and scientific resolution of this problem. Okay. And Euler was in Berlin at that time. He was Swiss, but he was in Berlin. And Euler took up this problem, And Euler started working out the motions of Jupiter and Saturn. So he had formulated the problem as finding out the equations of their path, and he had used those astronomical measurements to fit a curve there. And he again ran into the same problem as Boscovich was running into. Well, he didn't look at from the Boscovich's point of view as a problem of minimizing the sum of absolute deviation. For him, it was again just yet another problem of a system of inconsistent equations. So, but to a statistician, it's like an overdetermined system of equations. That's how we call it today, right? In those days, they didn't call it in that name. They called it a system of inconsistent equations. It's like more equations than the number of unknowns. How do you deal with that? That was the problem. Okay. So Euler faced the same problem, and Euler's suggestion was quite interesting. Euler said, okay, suppose I have 25 equations and only 5 unknowns. So then I will look at equations, groups of 5 equations, and I will try to choose the groups in such a way so that if the values that I get from each equation by solving each system of 5 equations, if they are reasonably close, I will be happy with that. But unfortunately, Euler was not successful in doing that with all the equations that he was dealing with. Okay? And then he sort of made again a remark like Boscovich was making. So Euler said that it again looks like to him a problem that has no hope, because the equations seem to be very not reconcilable. That's what he said. And he sort of washed his hands there. Nevertheless, Academy decided that he made enough contribution, and in 1749 he got the prize, because he had formulated the equations, but he really never solved the problem of solar system. Okay? But in 1749 he was awarded the prize. This problem was actually solved in a very so here is a picture of Euler. He worked on this problem in 1749. So you see that means that he was only 42 years old at that time. Okay? It's quite young. Okay? So it was not a solution, but he left most of the ingredients ready for the future scientists to work on it. Okay? So he worked out the equations, and then somebody had to reconcile those equations. That was the problem left for the future scientists. And the future scientist who solved this problem was Laplace. Laplace took up this problem, and in 1787 he had a very interesting idea. I will tell you about that idea later, but let me tell you what he found while handling this equation. He found that there is indeed some acceleration and retardation in the motions of these two planets. But it's not secular, or it's like, it is not unidirectional, it's actually periodic. So in fact, he calculated the period of this phenomenon, and it turned out to be, according to his calculation, about 900 years, which is fairly correct even with today's measurements and theory of the astronomers. Okay? So it's like, it's really a three-body problem. So when, for a while, some of these planets will be accelerating, and then when it reaches the maximum acceleration, then it starts retarding, and then it again starts accelerating, and it goes like that. That's how the motion is like. It was Laplace who first said that, so that is in some people call it, this is how he described the solar system. Otherwise, solar system is going to collapse, and we are all going to die, or something is going to happen. But how was Laplace solving this equation? Laplace, at the end of all his approximation and simplification, he had 24 linear equations in 4 unknowns. Now, he didn't take the path of Euler, who was trying to group these equations and solve separately and compare them. This is what Boscovich was also eventually doing. When he couldn't solve his own formulation, he solved those pairwise equations and then listed them. He somehow had this ingenious idea that he will form some linear combination of this equation. The first linear combination he took was, he added all those linear equations. That was giving him one final equation. Then he split those equations into 2 halves. One half containing 12, other half containing the remaining 12. And then he added 12, then he added the other 12 and took the difference of that. He never made it very clear in his writing why he was doing that, but if you go through it, it's actually clear that he sensed something there. Well, I will not have time to discuss all these things, but let me give you the idea here. Those of you here who know about the method of least squares know that when you solve the problem of least squares, you really don't solve a minimization problem. You solve a problem of linear equations, which you call the system of normal equations. Now if you think very carefully how this normal equation is really formed, that x transpose x beta equal to x transpose y, this is really, if you look at the original equation, x beta equal to y, we are forming some linear combination of them. Now Laplace's linear combinations were nowhere near what we call normal equations today. But somehow Laplace were convinced that that is the right thing to do. And based on that, the estimates that he got for the coefficients led him to this fantastic discovery. He saw that there is a periodic movement here. So this was one major breakthrough, though probably not a complete solution to the problem yet. Now, when Laplace started looking at Boscovich's problem, the first attempt he made, he thought that Boscovich's formulation is probably not the most appropriate one. So he decided that he will change the problem. He will not have sum of absolute deviation, instead he will have maximum of the absolute deviation. For some reason he thought that if he adds them up, that's not giving you the best fit. If you take the maximum, then you are sort of minimizing the maximum error, and that's the right thing to do. Now, when he started solving this problem, he could first solve it for n equal to 4. So for 4 points, Laplace could give a solution to his minimization problem. But if you go back to Boscovich's data, there were 5 data points because there are 5 cities. Okay. So Laplace decided that he will apply this method to 4 of those data points. Okay. Now if I go back, so you see here, in some sense you need some observation near the equator, so Laplace decided to keep Quito. He decided to keep Lapland because that is closest to the North Pole. Cape of Good Hope also he kept. Between Rome and Paris they are very close, so Laplace decided to discard Rome and have Paris. So that's what Laplace did in his first attempt. But he was not very happy. So after 6-7 years, Laplace came up with a better algorithm where he could solve this problem for 9 or 10 data points. But by then he realized that this is a problem that is probably going to be too difficult and is probably not meaningful or reasonable to look at it that way. Because if you have really a large number of data points, Laplace realized that he cannot solve this optimization problem. Okay. So here, and then he decided to go back to Boscovich's original formulation. And he was the first to give a major step towards the solution of this problem. This is how Laplace solved it. Laplace was very systematic in his writing, and this solution again Laplace wrote in a very systematic way, and I am here reproducing almost how Laplace described it as the historians report it. Okay. So Laplace said that let's take a simpler version of the problem. There is no x, no c, there is only an m, and if you want to minimize that, then minimizing m will be the middlemost y. We all know that. That is an elementary result in statistics. Then he said, okay, how am I going to minimize this? Well, he changed the problem by taking this x out. Putting that absolute value is not so important because in the problem there is sine squared theta, so it is all positive weight. And then he changed the problem like this, so then it is back to the same form as the original one. Okay. So Laplace decided to order these z values and according to the weight w, and then the minimizer will be the middlemost z value in that weight distribution. That was Laplace's solution to the problem without an intercept term. And then if you have an intercept term, Laplace essentially said something which was said by Boscovich partly. Well, Laplace said that we will assume that the line will pass through x bar and y bar, so we can knock out the intercept term and then this will be the problem. Now this is again not a complete solution to the problem because you don't know whether the minimizer of absolute deviation will actually pass through that point. This is an assumption that Boscovich was making and Laplace imposed that condition. So this is not something which can be taken as a complete solution. But this is how far Laplace could go, and Laplace left it there. Okay. Now, when Laplace was working on these, so this is what Laplace said around 1798-99. Okay. Now, by then in Europe, there was something else that became important. So by then, after the French Revolution in 1792, so French Revolution was over, and then they were changing a lot of things in Europe at that time. And one of the things they decided to change is this different measurement system. Okay, so they started developing the metric system. And when they were developing the metric system, they were looking for a standard for 1 meter, because you have to define 1 meter before you have a metric system, right? So how are they defining 1 meter? It's kind of very interesting. So this is how the history goes. So 1 meter was defined as 1 of 10 million parts of a meridian quadrant, which is the distance from the equator to the North Pole. So now that sort of brought back the problem of arc measurement again into business. Okay? So they wanted to get an accurate measurement of the meridian quadrant. And in 1792, Legendre was associated with the French Commission, which was charged with the measurement of a meridian quadrant, and the Cassinis were also involved with this work at that time. And Legendre invented and published the principle of least squares while working on this data and also some astronomical data. Actually, Legendre was working on both the problems, and he saw a connection between the two. Okay? In both problems, you have this system of inconsistent equations, and it was Legendre's idea to replace that absolute sign by the square. Legendre never gave any solid justification for it. See, he said this is a novel method that can be used and you can compute the solution. That's all he said. So if we go through Legendre's solution, so this is the picture of Legendre. Okay, maybe I should talk about Legendre's data a little bit before I go into Legendre's solution. Okay. So this is French arc measurement data, and I want you to carefully look at some of the things here. You see, I am copying it from a journal that has a German name. Okay, I cannot even pronounce that. Okay, and I see that most of the writers or historians quickly choose to call this journal AGE. So they refer to this as AGE. Okay, so this is in 1799 in AGE. There is a data on arc measurement, and you see the unit of measurement they are using is module. Okay, and one module is 12.78 feet. Okay, which is again not the French unit of measurement at that time. It is actually the German unit of measurement at that time, module. So there was a German involvement, and that's the interesting story here. But these are the points where they took the measurements. So from Dunkirk to Pantheon, Pantheon to Gauss to Carcassonne, Carcassonne to Barcelona, Barcelona comes to Spain. So if you look at the map, it's roughly like this. It's through the center of France. There is Barcelona, and this is Dunkirk, Pantheon, Gauss, and Carcassonne. This is how they collected the data. And to this data, Legendre was trying to apply his method. Okay. Now, why this German name? Okay, so let's go back to that table. Oops. So anyway, I think we can skip this part, because is there anybody here who doesn't know what is method of least squares? Probably everybody here knows the method of least square. I thought there will be people from outside who may not know least square, so I prepared one slide for that. So anyway, so this is method of least square. So you minimize the sum of square, and all of you know what is the solution. But the interesting point is this. I want to emphasize this point. If you look at the slope of the least square solution, it can be written like this. It's also a very well-known result given in most of the textbooks. So in some sense, those elemental lines, or the lines that join pairs of points, if you calculate their slope and take some kind of a weighted average, you get them. So it's like if somebody gives you Boscovich's table of pairwise solutions, from that you can calculate the least square estimate of the slope. That's the thing. Okay. And this is a point I want you to keep in mind, because I'll come back to that later again. So So let's go back to this table again. Okay. So this is a table, as I said, it appeared, this is actually a German astronomy journal. Okay. And at that time, the editor of the journal was a very famous astronomer, von Zach. And this is actually something that comes as a part of a note written by the famous mathematician Gauss. Okay. So Gauss sent a note to that journal where he was giving this data and giving some calculations for ellipticity apart, but no details. This was very characteristic of Gauss. Gauss will report the final results without giving the details in many places, and he was always right, almost always right. That was very characteristic of Gauss. So Gauss gives this data, that's why all these measurements are in module, and then he gives some calculation and gives the value of the ellipticity of earth. So now we have to spend some time on this question because this is again one of the principal characters in the history of least square. So Gauss comes into picture. Definitely he was doing something with this arc measurement data around 1799 as you see from the document. Okay. But that is not the only thing. Gauss was working on a separate problem where also he was doing something interesting which appears to be some kind of a least square. This is the other problem he was working on, which is actually something that really made Gauss very famous among the German astronomers at that time. So in January, February, this Italian astronomer Joseph Piazzi, he observed what is called a dwarf planet series. Now if you go back to my picture, okay, here is a picture of the solar system. You see between Jupiter and Mars there is this asteroid belt, and Ceres is one of the biggest asteroids in the asteroid belt. And this was one of the asteroids that was observed, and initially people thought this is probably a new planet, but it is really not a planet, it's really an asteroid. And what I gathered from my astronomer friends is that there is a NASA mission which has sent a spaceship to the Ceres to find out. This is something that is kind of important for astronomers. So there is a spaceship that has been sent out to Ceres, and it hasn't reached there yet. It will reach in 2015, so it's quite a distance. So this was observed only for 41 days, and based on measurements taken for 41 days, the astronomers wanted to predict the position and time of its reappearance. It got lost in the glare of the sun. People couldn't observe it after that. Now, many people thought that it is an impossible problem because we have so little data. To work out the orbit of the object, you need more data. That's what they thought, and Laplace was one of them. Okay. Surprisingly, Gauss did some calculation very quickly and made a prediction. And that prediction was somewhat different from what other astronomers are predicting, but Gauss was accurate. And what German astronomers started observing at that time, that Gauss could very quickly compute his predictions, and whereas it's like if you do the same computation using old methods like what Euler was doing earlier, if that will take probably more than 3-4 days, whereas Gauss could do that in few hours. So there is a mystery here, how Gauss was really computing there. And there is a good possibility that he was using something like least square and converting it into a problem of solving a system of linear equation. There is a good chance of that, otherwise how was he doing this computation so fast? And this impressed the German astronomers so much that in 1804 or 5, I don't remember exactly, so around that time he was made the director of Göttingen when he was only 27 years old. I mean, that's quite a prestige for somebody, and achieving that prestigious position at the age of 27 is quite remarkable. Okay. But in his writing, until 1809, he never used the term least squares, or he never gave details of his methodology. It was Legendre who in 1805 published his principle of least squares, where he gave the details, and Gauss published something in 1809 which he probably wrote up in 1807, but it took him some time to get a publisher for that because he originally wrote it in German and publishers wanted it to be written in Latin, so it got delayed by 2 more years, so it was published in 1809. But then history became quite interesting because Gauss always claimed in his writing least square as his method. He wrote main method S. That's his writing. Okay, and he said that he was using it since 1795. In fact, when this controversy started, when his book in 1809 came out, Legendre noticed it, and Legendre wrote a letter to Gauss, indicating that how could he say it his method because it was published in 1805 by him. Gauss, at the beginning, never bothered to reply to Legendre. But then, in 1811, Laplace wrote to Gauss. As a very interesting letter from Laplace. It's a short letter where he was essentially asking Gauss, can you produce some document where you have used this method? Now, not responding Legendre is one thing, but not responding Laplace was probably something that Gauss couldn't do. So Gauss wrote a very long letter to Laplace saying that, well, in there he actually said this, that he was using this method since 1795, which might very well be the case because this is the time around which this French arc meridian quadrant measurement data came out, and in 1799 he was writing something there and doing calculations. Okay? And so this was sort of the beginning of probably one of the most famous priority discourse in the history of statistical science, that who really invented the method of least squares. Now, in the next 5-6 minutes, I will spend on this controversy, and because it has some interesting elements in it, and I will also give you a solution to the least absolute deviation problem that sort of comes out of it, okay, in an interesting way. Now, one thing that the historians have tried is the following. Well, if Gauss was really using the method of least square, Gauss reported that table where he compiled the data. He also gave some computations with values. So if he was really using least squares, why don't you try to calculate the thing and see if you can reproduce Gauss's result by the method of least square. But the problem is not so easy really. If you actually apply simple least square, you don't get the values that Gauss was getting. There is another problem here. If you go back to one of my earlier slides, we started at some point there, which is a big assumption. See, for arc-length data, this is a linear approximation that was very popular in Europe. Everybody was using that for conic sections. Now, this is not the only approximation, of course. Okay? Now, was Gauss using that approximation or some other approximation? Gauss never gave any details. For Gauss, he was making prediction for astronomers. So, astronomers were happy if somebody makes a prediction for him and they can verify it to be accurate. So, no details was given. So, this was another thing. So, now this becomes a really interesting detective story. So, you need a Sherlock Holmes to probe into Gauss's work to see if you use some other approximations whether you can reproduce Gauss's result. Stigler has a very interesting paper that appeared in the Annals of Statistics where he actually tried that. He tried various approximations and computed things and trying to see whether he can reproduce Gauss's value. He never succeeded. And Stigler said that could be not Gauss's fault, that could be his fault because Gauss never said what approximation he was using. He never made it clear. Anyway, so this is where it stands. Now Gauss was using something, but nobody knows what it is. When he wrote in 1809 about least square, that's one of the famous work. We hear Gauss's name always with the method of least square. In fact, all the textbooks that we read about least squares that give all those theorems which are attributed to Gauss. People do not hear really so much the name of Legendre. Okay, it is the name of Gauss that we hear because he made tremendous contribution in the theory of least squares. Okay. And so, definitely he had a contribution, but was he the inventor? It's not very clear. But probably he had the idea. But interestingly, he had an independent idea in his 1809 work. So let's go back to the last question in the least absolute deviation. I call it question 3, which sort of was left out by Laplace. How to minimize this? In his 1809 work, surprisingly, he talks about that problem, and he says one of the elemental lines. What are those elemental lines? Elemental lines are the lines formed by joining pairs of points. He said one of the elemental lines is an optimal line. Again, a statement which is correct. Gauss didn't give any details. This was first discovered in Gauss's work by a historian of science. He is also a very famous historian. His name is Oskar Tscherning. Oskar Tscherning has published a lot on history of mathematical science. In one of his articles, he gives details about this. It's a very interesting article. So he writes what Gauss wrote, and then he gives a derivation of it, which we all know today. This is again a correct result without any proof given by Gauss. Well, how does one prove it? If you are interested in the proof, this is how. The proof is quite involved. It involves a linear programming formulation, and if you reformulate the absolute deviation problem as a linear programming problem, then it becomes something like this. So these Ri's are residuals, and this becomes something like this. And then, if you think about the simplex algorithm, what does it do? You have a linear programming problem, and you know that it lies in a convex polyhedron. So it is the optimal solution is going to be one of the vertices. What are those vertices? Those vertices are really those elemental solutions. That's how you prove it. So what Gauss says is right. Again, Gauss didn't give any proof. So I think I will conclude my talk with something that I read, and I was really quite impressed by the style of writing. So I will read a part of Stigler's paper where he was discussing this historical controversy. Okay. So this controversy went on between Gauss and the French school for about 15-20 years. Okay. And the last letter that Gauss wrote there at one, in fact, for a while Gauss was quite persuasive. In fact, he was writing, there is a very interesting paper by Plaquet which appeared in Biometrica, where he quotes from many letters of Gauss and his German astronomer friends, where it is clear that Gauss was sort of persuading his German friends to vouch for him, to advocate for him, saying that he discussed this method with them. But surprisingly, these astronomers are somewhat lukewarm about it. Okay, there could be one reason for that. Probably they didn't understand what Gauss was telling them at that time about the mathematical details or computational details. Okay, so they didn't quite explicitly vouch for him. And Gauss could never produce any written documentation, and Gauss in many places said that I write many things in my notebooks that I don't publish because I don't believe in publishing until the idea is ripe. Okay, so he said such things. Anyway, so this is a very interesting statement by Steve Stigler, who is one of the famous historians in statistical science. So this is what Stigler wrote about least squares. The method of least squares is the automobile of modern statistical analysis. Despite its limitations, occasional accidents and incidental pollution, it and its numerous variations, extensions and related conveyances carry the bulk of statistical analysis and are known and valued by nearly all. But there has been some dispute historically as to who was the Henry Ford of statistics. So who invented car? That's what he is saying. And so this is the paper where he was trying to reproduce Gauss's result by various nonlinear linear approximation. Okay, but he couldn't succeed. So obviously, as I said, Gauss's contribution in the development of least square is immense. Okay, without Gauss, probably least square theory would have not succeeded. Of course, Legendre had the fantastic contribution that it first gave scientists a method to compute the solution, and they could use it, and which was giving them results that worked. So this is what he writes at the end as a sort of a verdict. When Gauss did publish on least squares, he went far beyond Legendre in both conceptual and technical development, linking the method to probability and providing algorithms for the computation of estimates. His work has been discussed often, most recently by Searle, Eisenhardt, Goldstein, Sprott, and I mentioned Oskar Tscherning. But much of this development had to wait a long time before finding an appreciative audience, and much was intertwined with others, notably Laplace's. Gauss was the first mathematician of the age, but it was Legendre who crystallized the idea in a form that caught the mathematical public's eye. Just as the automobile was not the product of one man of genius, so too the method of least squares is due to many, including at least two independent discoverers. Gauss may well have been the first of these, but he was no Henry Ford of statistics. That's his verdict. if there was any single scientist who first put the method within the reach of the common man, it was Legendre. Okay. So that's why we are here. And I think I will end my lecture here. This is not my opinion. I thought I will sort of give you an overview of this idea. I tend to believe that if there were ever a Nobel Prize for least squares, Gauss should at least share that. Okay, he should get it. So I think I will conclude here. Thank you for your attention.
Well, thank you, Professor Chaudhuri, for a very interesting talk. It is actually a quick course, a short course in the history of mathematics, and in particular the history of least squares. It's a fascinating story. I never knew that behind the story of least square there are so many figures involved in this. I'm sure Professor Chaudhuri will be happy to answer some questions. Are there any questions, comments?
So do you have any insight as to why nowadays textbooks attribute Gauss as the least squares inventors or not Legendre?
See, I think those theorems that you teach, those were all due to Gauss. Well, Gauss never talked about unbiased estimates. For him, unbiasedness was a set of equations. Okay, so he said the optimal solution, if you put those constraints, must be this. That sort of formulation. So that best linear unbiased estimate result was done by Gauss. Okay. And by the way, I should say this, that we often refer to many of these results as Gauss-Markov theorem. Markov really did that much later. Markov was born after Gauss died, so there was absolutely no collaboration between these people. Markov sort of independently invented some of these results, and it got tagged with his name because of the writers later. Okay, but Markov was not the originator of this result by any means. It was Gauss who gave the comprehensive theory of least square. He connected it with the normal distribution, theory of errors, everything. So I think that is the reason. Okay. Because except giving the method and its solution, Legendre didn't do anything about it.
So the least squares name.
That's due to Legendre.
Is that due to Legendre?
That's due to
Okay.
Legendre. Principle of least square, that's due to Legendre.
So I actually wondered why you did not talk about what the most important points that concerns us today, that median regression was there before mean regression.
Yes.
So actually
It is
was extended
very
to-
well known to people who work on quantile regression and
Yeah, it's
absolute
quantile regression. It said all the things that it's a very nice example of a mathematical, let's say that mathematically clean and easy theory took over.
It is more natural.
For
It's more
200
natural.
years, and we suffered. We lost robustness and everything. So we kind of took us 200 years.
Because Laplace could not solve it for you.
Yeah. Just because the problem was easier to solve.
Yeah, it is probably, absolutely. And there is no reason to put a square there,
Right.
except that. And Legendre also didn't give any reason to put a square there except he could compute the solution, which impressed everybody, because everybody then had their system of equation, they could compute the solution.
Did Legendre or Gauss worry that the solution to this absolute deviations problem is not unique?
Gauss didn't say anything explicitly about that. Legendre, I don't think ever spent much time on some of absolute deviation problem. At least I don't know that. I have not seen any.
So nobody mentioned that the solution is not unique. Not necessarily, does not have to be unique.
Yeah, it doesn't have to be unique, definitely not. But Gauss gave a characterization of one of the solutions. That's all. He said that one of the elemental solution. He writes like this: that if you choose the equations properly and solve it, the exact solution is the solution. That's what he said. That's his language. And Gauss was very young when he was highly recognized. So he probably didn't know this game of obligation and the politics involved in that well. I mean, priorities and such things were different for him. For him, solving the problem and presenting the solution was the ultimate goal. Okay. So he is always very cryptic in his writing. But his results are all, I mean it has been high. Everybody said that he was always correct. But the term disk he never pronounced except in his 1809 book, where he used that and where he called it his method. And that 1799 paper, where he has a table of data and some numerical values, he actually after a month he publishes a correction saying that one of the arc length measurements are incorrect, so that has to be corrected, and he produces a corrected value for the ellipticity. Our first value was 1 over 150, the next value was 1 over 187, but none of these values Stigler could reproduce after a lot of tries. So definitely he was not using least square the way Legendre recommended it at that time. But how he was producing those fast solutions for astronomers is a mystery. Astronomers said that what would take by Euler's method 5 days, he would come up with a solution in 3 hours. So he must have a fast, and those are fairly accurate. The astronomers verified them. So that means it was calculating the orbits pretty accurately.
So before we end the session, I would like to present to Professor Chaudhuri token of appreciation. This is
Thank you.
some souvenir from IMS.
Thank you very much. Thank you.